Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be finishing our Chapter 2 notes, where we're looking at Section 2.4, Chemical Reactions. Now, in earlier sections, we talked about physical and properties as well as physical changes. In this section, we're looking at chemical properties and chemical changes. One of the things you really should be able to do is understand when you have each of the four situations. Now, a chemical property is the ability of a substance to undergo a specific chemical change. Now notice it says ability. That doesn't mean we're actually chemically changing it. It means we're describing a chemical change. So if I talked about I'm going to burn a piece of paper and say paper is flammable, that would be an example of a chemical property because I didn't actually burn the sheet of paper. I'm talking about the ability of paper to react with oxygen in a combustion reaction. So that's what a chemical property is. And remember, all it's really doing is describing how a substance chemically reacts. Now, an example would be, and you see a picture of iron rusting here, iron is able to combine with oxygen to form rust. This would be a chemical property of iron, that it reacts with oxygen to form rust. Now, if it actually happens, I'm not talking about a chemical property anymore, I'm talking about a chemical change. But saying iron is able to, or iron will rust when it reacts with oxygen, now I'm describing a chemical property of iron. Now, if I have a substance that doesn't react with oxygen, its inability to react is still considered a chemical property. So I'm talking about it potentially changing into a new chemical through chemical reaction. So the big difference between chemical versus physical is we're really describing a change in chemical identity in a chemical property or chemical change. Now, there is a movie that I want you to watch dealing with physical and chemical properties that go through and look at a variety of different physical properties of substance, and they describe it and show them all, as well as a variety of different chemical properties of substance. Now, when we go from a property to a change, now we're actually looking at when the process occurs. So a process where one or more substances change into new substances actually change. So we're not describing the ability to do it, but we're actually describing the fact that it happened. Then we're talking about a chemical change. And remember, it's a rearrangement of the chemical identity of the substance. So how do you know if a chemical change has occurred? Well, there's certain indicators, and these aren't perfect, but they're a good general indication that a chemical reaction has occurred. And this is something that we're going to use in future chapters as well. So this is a basic idea you really should understand. When did or when I'm watching a situation, are there any indicators that something chemically has actually occurred? Well, first would be a color change, like in the case of a precipitate forming. I've got a clear solid liquid or a clear colorless liquid in the top beaker and a clear colorless liquid in the bottom beaker. And when I pour the two together, all of a sudden out of nowhere, this yellow solid appears. Well, that yellow solid formed from a liquid being mixed with another liquid, is what's known as precipitation. So it's actually a solid forming inside there. And we've got a definite color change. We had no color before, and now we've got a yellow color. So that would be a good indication that something chemically changed. Because remember, your color is tied to the chemical identity. And when you change your chemical identity, you might be changing your color. So while color is a physical property of the substance, it's actually tied to the chemical identity of the substance. And when the identity changes, you may have a color change. Another good indication that you have a chemical reaction, or I should say that you probably have a chemical reaction occurring, is when we're looking at a odor or a gas being produced. Remember, once again, odor is tied to the chemical identity of a substance, and if I smell something new, it's an indication that something chemically changed. Typically, what's happening is we're producing a gas, and that gas has an odor. In the picture you're seeing here, this is actually a penny reacting with nitric acid, and you're seeing a brown gas coming off of the penny. Highly, highly, highly toxic, would kill you if you inhaled it, um, but obviously a chemical reaction occurring here. So in this case, we have a gas being produced physically. You've got those bubbles, and that's a good indication you got a chemical reaction. And then finally, when light is produced, or when you have energy in the form of heat coming off something. So large amounts of heat being reduced, or light are produced, or light being produced, good indication that you have a chemical reaction. Combustion is a good example of a chemical reaction that we've all seen, something burning. As it burns, you've got a change in color, and you also have light and heat being given off. Good indications that you have a chemical reaction occurring. Now, this is an example of a chemical reaction. Hydrogen reacting with oxygen to form water. So one chemical property of hydrogen is that it can react with oxygen to form water. If I actually combine hydrogen and oxygen to form water, now I'm describing a chemical reaction. Now, when I write this chemical reaction, this is something you should be used to seeing. I have my starting substances on the left, and in chemistry, we call those starting substances reactants. And on the right side of that arrow, which is my yield sign, which separates my reactants from my substances being produced or products, I have products. So a chemical reaction is often described in this way. Left of the arrow reactants are starting substances, right of the arrow what ends up being produced. And in this case, we only had one thing produced. We had water in this chemical reaction. So you should understand rudimentary what a chemical reaction looks like and where the reactants and products are. Now, one thing that's true of all chemical and physical reactions is what's known as the law of conservation of mass. So this is one of our laws of chemistry. Remember, a law is a description of what happens, not why it happens. So the law of conservation of mass says that in ordinary chemical and physical reactions, mass can't be created or destroyed. Now, we're not saying why. All we're saying is that when chemical and physical reactions occurring, the amount of mass or matter isn't changing. So we're not actually changing how much it weighs. So we're not creating or destroying new things. And that's because the why behind this is actually all we're really doing is rearranging our atoms. We're not creating or destroying them. We're putting them together in new combinations. But what the law really says is when I have a chemical reaction, the mass that I start with has to be the mass that I end up with. So the mass of the reactants have to equal the mass of the products. And this is some basic math. We're not doing real math in chemistry until we get to chapter 3, but this is a mathematical application, so we do have to do a little rudimentary math here. Now, I've got a short movie that deals with law of conservation of mass that I want to make sure that you watch online because it really does show on a particle level what's happening with law of conservation of mass. But really, what I really want to do to finish up the notes here is to take a look at an example and how you would handle and show law of conservation of mass. Now, a reaction between sodium hydroxide and hydrogen chloride gas produces sodium chloride and water. So it's describing a chemical reaction. Now, a reaction of 22.85 grams of sodium hydroxide with 20.82 grams of hydrogen chloride gives off 10.29 grams of water. What mass of sodium chloride is formed in the reaction? Well, if the law of conservation of mass is true, and we have the perfect amounts of these things reacting to show that it's true, what you really need to understand is what this looks like as a reaction. That's going to help us track reactants and products and show law of conservation of mass. So the first thing you have to do is write out the word equation. So you're going to take what's described up top, which is the description of the chemical reaction, and you're going to make it look more like we write chemical reactions. Reactants on the left, products on the right. Now it says a reaction between sodium hydroxide and hydrogen chloride, so that means those are our two reactants. And then it says it produces, so to the right of the arrow will be sodium chloride and water. Now at this point what you need to do is pull our masses out that it describes. Now it says 22.85 grams of sodium hydroxide. So that's how much sodium hydroxide I have. It's reacting with 20.82 grams of hydrogen chloride. So that's the mass of my hydrogen chloride. And it also says I produce 10.29 grams of water. Now, remember, law of conservation of mass says the mass of the reactants equals the mass of the products. So let's turn this into a mathematical expression. 22.85 plus 20.82, that would be the total mass of my reactants, and that has to equal the total mass of the products, which would be my sodium chloride, which I don't know, plus 10.29. So at this point, all I have to do is solve for my unknown. So picture sodium chloride as our x. Solve for x. So I add the two things on the left and I get 43.67, and that's going to equal sodium chloride plus 10.29. If I subtract 10.29 from each side, I'm left with a mass of sodium chloride. So 43.67 minus 10.29 ends up 33.38 grams. So this is a way in which I could apply the law of conservation of mass. Since I knew how much I started with, and I know that they completely react together, I can predict the mass of the missing substances on the right. And that ends our notes over chapter 2.